Hello and welcome everyone to our fifth session in the Fault2SHA learning series. As always, the purpose of this series is to really help all of us working in using faults in seismic hazard assessment. Hello and welcome everyone to our fifth session in the Fault2SHA. I'm speaking to myself. Welcome everyone. It's the purpose of this session is really to help everyone working in using faults in seismic hazard assessment to make sure we can understand the topics in different fields and bring us all together, so we really can, when we're listening to research talks, when we're reading papers, make sure we have an understanding of the basics and understanding of the fundamentals, so that then we can collaborate better. And this week, to really help with that, we have Laura Peruzza, who's going to be talking about false friends in seismic hazard assessment. So she's going to help us clarify a lot of terms that get used, misused, understood in different ways. So I'm really excited to hear what Laura has to say. For those of you who don't know Laura, I'm sure most of you do. She's been a member and led many national and international projects relating to seismic hazard. She has an incredible research output. She's been cited over 1,750 times, and lots of us have cited her many times. So her work is very important. And I know personally, when I've collaborated with you, Laura, it's really helped me be honest and be a good scientist. You always ask the difficult questions. So I really appreciate our collaboration. So with that, I welcome everyone to this session, and particularly I welcome Laura and look forward to your talk. So thank you, Laura.
Thank you, Joanna. Now we have to try to share the screen. That was the trick we did before. Hello, the camera.
And just while Laura's getting started, she will be presenting her presentation, and there will be some time at the end if any of you have questions. So if there's anything else you want clarifying, do ask at the end of the session.
So here we are. Do you see my presentation?
Yes, all looking good.
Okay, thank you for the introduction, Joanna. You are so enthusiastic, but I don't think I reached the level that you mentioned before. I'm happy to be here today. It's 4 o'clock in Trieste, where I'm talking from. Summer is coming. There is a little smell of summer after this tough winter. And I want to present you something that is something different from a traditional lecture. You do not have to wait for a traditional presentation with method, data, and results, because my presentation will be sharing with you some of the assumption we have behind the seismic hazard assessment, and as Janet said before, the misuse of some terms that do have different meanings depending on the community you belong to. The idea of this lecture started 2 years ago. We were in Barcelona for the 4th Fault2SHA workshop, an exciting one. The last one we did live, unfortunately. Then we had another one via internet because of the pandemics. And during that workshop, we decided that it was necessary to start writing a glossary, a dictionary, for explaining the different meaning that the same terms has in the various disciplines. So the idea was there, but the time is always too short, and the job went aborted. And I decided to take the opportunity of this lecture to start this kind of little glossary, little dictionary that we can share. And the idea is that we can build a common jargon, and we can try to share and deliver the best possible ingredients for seismic hazard analysis only if we speak the same language. So I will enter into the lecture with some basic of the seismic hazard assessment, and then I will try to touch some false friends in my opinion, of course, for friends. Let's start with a very general concept. Hazard is different from risk. If there is a lesson learned with the pandemic, is that definitely hazard is not the risk. And the picture concerning earthquake, seismic hazard, explaining quite clearly that hazard is a component of the risk, and the other components are the vulnerability and the value we give to our city, to our towns. And the combination of these ingredients gave the risk. But do we have really a definition for seismic hazard instead of saying simply a component of the risk? Well, I try to collect some definitions that are available in various sources, and I will comment them with you. And perhaps you will have at the end some additional suggestion of definition of what seismic hazard is. So let's start with the generalist sources, and there is Wikipedia, the website of USGS, the website of the Italian Civil Defense Department, that is the main agency funding research concerning risk and hazard assessment and reduction. And of course, these are sites that deliver the message to non-specialist public. The first definition by Wikipedia says that the seismic hazard is the probability that an earthquake will occur in a given area with a given window of time with the ground motion intensity exceeding the given threshold. Well, if you look at the sources of this definition, it is a Canadian sources. At the moment, I consulted Wikipedia. The original sources was not available, but you can clearly reckon that this kind of definition is a sort of caption of the map we usually have around for representing seismic hazard. There is a slight difference because they mention hazard as the probability with a ground motion level. Instead, we usually have a map representing a ground motion level with a given probability, but it is a minor difference. Moving to the definition given by USGS, well, I think it's a bit a tautology, a loop around the same word. The seismic hazard is the hazard associated with potential earthquake. Well, it's not particularly informative, in my opinion, because it does not tackle the core of what seismic hazard is. And if we go to the Italian source, we have a different start. Seismic hazard is given like the frequency and force of an earthquake, of earthquakes, in some kind, we say the seismicity, but then you go back to the first definition, defining the probability again of something. The something is more blurred now because the definition mentioned the threshold of intensity, and probably they refer to macroseismic intensity, that is a measure of the effect of an earthquake, magnitude, that is a characteristic of the source, and peak ground acceleration, that is a particular one of the possible ground motion measure. So if you fear that there is a translation problem in the Italian source, I can assure you that the Italian version states exactly the same. So I resorted to more technical, let's say, more technical documents, and we started with documents released by engineer in 1984. The Earthquake Engineering Research Institute defined the seismic hazard in a broader way, any physical phenomenon, ground shaking, ground failure, that is associated with an earthquake, but they limit the definition of seismic hazard to the fact that they may produce adverse effect on human activities. So in some way, if there are no humans, there is no seismic hazard. It's something more related to the risk than simply to the hazard. The Encyclopedia of Geology in 2005 defined again the seismic hazard as the effect of earthquakes that can cause damage to the built environment. Again, the meaning is restricted to the concept of damage and to the existence of some built environment. But they enlarge the possible effect to ground shaking, ground rupture, secondary effect, liquefaction, landslide. It's the point of view of the geology, of course. Then there is a paper, a presentation done by Wang. He is a seismologist, geophysicist. Perhaps in those years he was at a turning point of his career. And he broadened the definition of seismic hazard, including the natural occurrence of earthquakes and the resulting ground motion and other effects. So the definition is larger. It includes both the definition of seismicity and the effect that this seismicity can cause, but no mention to human and damage threshold is in there. And finally, there is the definition given by Kiko, great statisticians, that in 2014 assign the seismic hazard for seismic hazard any physical phenomenon that is associated with an earthquake. So again, a larger spectrum of phenomena, and their effect on land, man-made, and socioeconomic system that have the potential to produce a loss. Again, the concept of a loss and then a risk concept is introduced. He finished the definition by saying that we can also discard the loss and indicate the probable level of ground shaking occurring at a given point with a certain period of time. So you see, the definitions are many, and probably none of this definition is completely satisfying. I like more the definition given by Wang, probably removing also some words to this very broad definition. Intrinsic natural occurrence of earthquakes eliminate the possibility to estimate the seismic hazard, for example, for induced seismicity. That is one of the, let's say, leading topics in the last year. So if you want to collect additional definition and you want to help me to find a common definition valid for all of us, this will be an exit of this lecture, for example. Once we have defined the seismic hazard, well, we have to assess them, and there are two main kind of approaches that are often used for assessment, for assess the seismic hazard. We mentioned the probabilistic approaches and the deterministic approaches, thinking that there is such a kind of wall between them, but in reality there is not a wall between the two kind of approaches. And this is well written by Abramson, that in 2006 wrote in a, let's say, review paper, there remain widespread misunderstandings of the two methods by engineers and earth science professionals practicing in earthquake engineering. So also the definition of what is probabilistic and what is deterministic is somehow blurred. We can say that is deterministic if we have individual earthquake scenarios. There are words already taken from the paper for Abramson. Using a specified ground motion probability level, the largest ground motion is usually taken, considered for designed ground motion. And on the probabilistic side, we have all the possible magnitude and location combination, as well all the possible ground motion probability levels. So we have to include in the set of scenario only physically possible earthquake. So also the definition, the division between probabilistic and deterministic approach can be somehow reconsidered. In any case, the two classes survive, resist. Probabilistic approaches were mainly used after the 70s of the last century for seismic resonation purposes. Deterministic approaches were preferred for nuclear power plants, strategic facilities, mainly before the 80s. In the new century, probably we are facing a new combination of the two ingredients where and probabilism in sources is applied by deterministic modeling of ground shaking and vice versa. I propose here you the classification given by Morwood in 1993, because in some way his distinction in 5 generation of seismic hazard assessment is quite important. Is a good way of seeing the problem. And we will scroll through the five generation, better to the 4th generation, and we will see which are the basic assumptions that are behind each kind of method. We start with the 1st generation, historical determinism. The basic idea is that we do expect in the future what we have observed in the past. In Messina, southern Italy, there was a magnitude above 7 in 1808. We do expect in the future at least a magnitude above 7. About the death that were caused by this earthquake, of course, we have the capability of reducing this huge amount of death by working on the vulnerability stuff and on the alert condition for tsunami, because the earthquake was followed by a tsunami too. If we move from the historical determinism to the historical probabilism, well, there are not such a huge difference, except we start to play some statistics on the observation. We can forecast the future from what we have observed in the past. And so we still may have limited assumption on the sources, only the observation, the historical observation of what has been occurred in the past. We do have a simple propagation model or interpolation of the effect from one point to the other, but there is some statistics, and several methods have been proposed in the last 50 years, starting from the extreme value approach proposed by Lomlin and Epstein using the Gumbel distribution, till the macroseismic site intensity method proposed by D'Amico and Alborella in 2008. The introduction of some statistics make the forecast, make a level of certainty in the forecast and give a time frame to our estimate that the historical determinism has not. Because we cannot travel in these days, I want you to do an instant virtual visit to Venice to see what the result of these 2 first generation of seismic hazard in Venice. Venice is quite far from relevant earthquakes that in Italy are located along the Alps and along the Apennines mostly, has a long time history, and this longer history enable to have us a very populated site intensity history that is represented in the graph. And from that graph, if we accept the fact that macroseismic intensity is an estimate of ground motion, we can derive an evaluation of the ground motion in Venice. According to the historical determinism, we may have an intensity maximum of degree 8. I remember we are dealing with the Mercalli-Cancani-Sieber scale that is ranked on 12 degrees. and the 6 is more or less the first damage threshold. The intensity maximum observed is 8 because you know half degrees are not allowed in the definition of the macroseismic scale. There is no intermediate ground motion level at 7.5, but only the uncertainty in which level, which degree the intensity is assessed. If we move to the historical probabilism, well, Vera D'Amico prepared me another curve, and what you have in the curve is the probability of exceeding in 50 years the various level of intensity that are plotted along the x-axis. And we may refer to this curve to say, for example, that the 10% probability in 50 years is exceeded if we have at least an intensity 6. So the two first generation went into the trouble when we realized that something probably were missed in the past. The duration of the instrumental catalog, the duration of the historical catalog is probably not sufficient to have all the seismic cycle represented and several other disciplines enter into the game to put additional constraints. And it was in this sense that we enter in the third generation, what we call seismotectonic probabilism, that state that we can forecast the future if we can model the reason why earthquakes occur and how they propagate. There are some assumptions that are the pillars of this third generation: define the source and the potential of earthquakes, model the ground motion propagation with uncertainties, accept some assumption on the process itself. But I want you to go back to the fathers of the third generation seismotectonic probabilism, that are Aline Cornell and Luis Esteva. Probably we all cite the Cornell paper, but I suggest you to read again the review paper done by Robin McGuire in 2008, because it's a very entertaining story about the life of these two young men that in the United States and in Mexico at the beginning of the 60s started to develop what will be, what is in the future the standard mathematical formulation for doing something. The word enlightened here, basis for choosing the seismic design level around the world, are very, very important in my opinion, because they explain the reason why the paper of Aline Cornell, that we often quote, reference in our paper, is a seismic risk analysis and not seismic hazard analysis. As I was thinking at the beginning, well, by choosing a seismic design level around the world, you are fixing in some way the vulnerability and then the risk result you have. And this is the reason why the paper is titled in this way. Nowadays, the third generation seismotectonic probabilism is the standard for all over the world. The Mosaic model done by GEM, here represented, is mainly based on this generation of seismic hazard assessment, and this generation has some key assumption that we will scroll in a while. The seismicity has to be homogeneous and uniformly distributed inside the source. The magnitude frequency is a Gutenberg-Richter law, is a log linear relationship, and earthquakes are independent events, and their occurrence is stationary in time following Poisson process. So each one of these assumptions has something that introduced me the term fault friends. That means some terms that have been used and abused in the different community. Fault friends in the sense that we say the same word, but we are thinking to a different object. Let's start for the fault friend one, that in my opinion is the concept of a seismic source as a homogeneous and uniformly distributed source. So starting from the very first definition done by Cornell in 1961, where faults were simple lines and the points and area sources were annular sources representing the distance with respect to the site. Moving to a more geologically oriented definition of sources given by Reiter in 1919, where faults were objects reckoned in the field, recognized by surface data or from indirect data like geomorphology or geophysics. Seismogenic structure, where diffuse active faulting can be treated in a single area as a single source, ending up with the seismotectonic provinces, where we have a wide region having the same seismogenic potential to be assigned. Well, till the very last definition given by OpenQuake, the engine we are using right now to compute the hazard in 2021, that subdivided sources in parametric and non-parametric sources. And between the parametric, when you are dealing with the area and fault sources, well, the assumptions are usually always the same. Seismicity is homogeneous and uniformly distributed inside the sources. Well, when we define as seismogenic sources, we have to accept that any point inside it is equally likely to host earthquakes with a given occurrence rate, with a piece of those that goes into the field and try to detect lateral variation of something, for example, along a fault. The image here is the Monte Vettore fault after the 2016 earthquakes, photo provided by Lucilla Benedetti. When we define a seismic source, we accept this assumption. And it was quite simple, the mathematics for Cornell in 1968. He had a 650 kilometer long fault system. He had a Gutenberg-Richter relation calibrating on a cathode that was something less than 2,000 years long. And he computed the rate of magnitude greater than 5 earthquakes per year and per kilometer. All the full system is equally characterized by the same rate of occurrence. We do more or less the same, even by using much more complex situation. Right now, this is a model of the fault that caused the seismic sequence in central Italy in 2016. Of course, one of the possible model. The model is shown in the lower corner of the picture. Is a complex surface that is broken at the surface but is continuous at depth. And when we try to do some computation with this complex source, we may assume uniform seismicity all over the fault. And this is a basic assumption. We have to decide if we keep on going or not. The reason why the figure is tilted is this one. We may have different criteria for defining the sources. For example, this is the database of the individual seismogenic sources for the same area that define composite seismogenic sources with different orientation, different elongation. No matter how we define the source, but we have to write what we call something seismogenic sources. Well, be ready. Probably models of seismic hazard like that earthquakes occur on that, inside, on top of them, only on that. And probably they will assign a uniform distributed seismicity to it. Till when you explicitly say, please don't do that, treat the sources in a different way. So this is the reason why I think that seismogenic source is some kind of false friends in our community, because for seismic hazard modeler has a meaning. Most of the other discipline represents something else, a description of the rupture, a description of the fall of the earthquake cluster, not necessarily respecting the assumption of the seismic hazard assessment, the traditional, let's say, seismic hazard assessment. There are, of course, other alternatives on that vision, and I hope we have the time to talk about that later on. The two other false friends are related to another assumption that we accept in seismotectonic probabilism. Earthquakes are independent events and the process is stationary in time. The two red words may be, in my opinion, that may lead to some friends between the different communities. Well, what is best than a motorway than cars for representing a process where we have independent event and something that is stationary in time. There are reasons why this assumption has been adopted. The first reason is that seismotectonic probabilism want to take care of the long-term tectonic loading. Long-term tectonic loading is taken into account, and it is thought that the annual average rate of earthquakes is invariant in time. The second reason has to deal with the exit of a seismic hazard assessment, what is going out from the process. And I refer to the regulation purposes that the seismotectonic probabilism has. Seismic zoning has to be independent from the year of application. We cannot change the seismic zoning after each earthquake occurrence. And so the stationarity in time is a main requirement that accounts for these two factors. But of course, earthquakes are not independent events. Again, showing the example of central Italy, where we can say that earthquakes are independent above a given threshold of magnitude, for example, the magnitude greater than 6, or if the patches of the rupture are not overlapping, and so there are different parts of the faults that are related to the earthquake. And again, is the sequence in 2016 independent from another sequence that occurred a few kilometers southward 7 years before, the L'Aquila sequence? Earthquakes are definitely not independent event, even if we see the stuff at a larger scale. Here, for example, is a super recent publication that quote the recent Japan earthquakes like aftershock of the great Tohoku earthquake in 2011. And so if they are aftershock, they are not independent from the main. Usually seismic hazard analysts solve the problem with the clustering. The clustering algorithm are used to remove earthquake from the catalog so that we may obtain some independent events. Here you have an example of some different algorithms used on central Italy. The sequence of 2016 is just at the end of the time scale. Of course, we have difficulties to handle complex sequences, but one fundamental problem that is often neglected when we are doing this kind of exercise is the fact that probably we are losing something by doing it. Cutting the branches of our catalog, cutting the dependency of event, are we really accounting for the long-term tectonic loading or not? This is one of the reasons why I put the word independent event into the false valence category, because for seismic hazard modeler, independent events means something true at the classical sequence, let's say, stationary in time. While for the other expertise, independent events are probably earthquakes that have no causal relation among them. Let's go back to the word stationary in time. Is stationary something that has an average occurrence rate that do not change in time? Is stationary the arrival of cars at an intersection, as already said? The average occurrence rate is what we call return period, and is something that we use to fully characterize the Poisson process. So I don't want to enter into details of statistics, but Poisson process is handful, because with a discrete distribution, it can model the number of occurrences, and with a continuous distribution, the exponential distribution, it can model the interval time between consecutive events. And so it is particularly useful in our case, because we can deal with a simple function to compute probabilities. In addition, Poisson process can be stacked, and when you have several Poisson processes, the sum of them can be considered again a Poisson. So let's see what happens in the community when we talk about return period, that, as defined before, is the inverse of the average occurrence rate. When we are dealing with cars, well, it's simple. The return period is the mean value of intertimes between two consecutive cars. If we see the definition of return period again in USGS website, in terms of geology, in terms of, for example, paleoseismological analysis, well, again, return period is the average time span between earthquake occurrence on a fault or in a source zone. Well, the two definitions are identical, in my opinion, but for a strange reason, when we go to the hidden, let's say, hidden meaning that we give to this word, we have in cars the situation that we acknowledge. It is a random process where the expected value is equal to the variance, while for some strange reason in geology is a periodic process where the variance tends to zero, and the stress accumulation, look at the picture that is given together with the definition of return period. Look at the picture. The stress is accumulated till when an earthquake occurs, and this idea of regularity, of periodicity, is exactly the opposite we have when we are talking about random stationary process modeled by Poisson distribution. So the problem is still more complicated, because when you are looking at an hazard map, you are not referring to the frequency of an earthquake. You are referring to the ground motion level. So those awful and simple equation that state the probability of exceedance with respect to the observation time, t, small t, and the return period, capital T. Well, the probability of exceedance and the return period is referring to the ground motion level. So we have to take into account that the ground motion level is not strictly related to the frequency of earthquake, but also to the distance of the earthquakes with respect to the site. The extreme ground motion is not controlled by the occurrence of rare event, but more by the variability of the ground motion prediction equation. And to show you analytic example, I resorted to a slide given by Strasser in 2004, where she listed, well, two simple cases to demonstrate that rare motion drive the hazard at longer return period, not rare earthquakes. So a magnitude 6.5 with a recurrence interval of 50 years. If we take the ground motion level at 3 standard deviation, well, we have a frequency of exceedance that is representative of a return period of about 50,000 years. While if we are considering a magnitude 7.5 with a recurrence interval of 1,000 years, and we take the mean, the median ground motion frequency of exceedance 0.5, well, the return period of this event is only 2 years, 2,000 years. So the combination of these different ingredients in hazard make me think that we say we are working in a probabilistic framework, but at the end we think in a deterministic way, and the people that discover a new big earthquakes on a fault, for example, want to see the impact this event has in the hazard map, and often this is not the case. So this is the reason why I enter return period in the list of the false friends, specifying that probably we have to be more precise, more clear, inter-event time of what we are discussing, of frequency of earthquakes, of ground shaking, of something else. It is something that is often misused between the different people that work around the seismic hazard. In reality, I have a fourth false friend that is related to the term peak ground acceleration and the confusion that is often done with the maximum acceleration. I don't know if it is a problem particular of Italian language, but I would like to give the floor to some engineers to face this possible false friends in a future lecture for the learning series. So we can solve in some way the problems of false friends. Well, I think that the transition from the third to the fourth generation of seismic hazard help us in doing that. The fourth generation of seismic hazard is defined by non-Poissonian probabilism to include all we can handle without resorting to Poissonian processes, but also not resorting to uniform distributed seismicity. Some assumptions have been relaxed in the fourth generation. For example, the seismicity cannot be can be no more homogeneous and uniformly distributed inside the source. The source become smaller. The segmentation and zonation can be less rigid. The magnitude frequency is not only controlled by a Gutenberg-Richter relationship, but we can enter different kind of magnitude frequency relationship or introduce different model for relating the frequency and the magnitude of events. And similarly, the process in time do not need to be stationary anymore, but we may account for some time dependencies or for the aftershock sequences as well. A great step forward for this new picture, it was related to the implementation of new computer engine, new procedural scheme. I remember that SHA was the first, in some way, abandoning the terminology of seismogenic sources in terms of source model given by an earthquake rupture forecast, where we list the probability of all possible finite rupture events that in a region and in a time span. And even if the difference seems not so huge, in reality, the difference is huge. And we can so abandon the term seismogenic source that implies uniform distribution inside. Other implementation has been done by other computer code. I do not remember if it was Crisis or another software that for the first time accounted for generalized non-Poissonian processes. There are implementation linked to the topography, to the liquefaction, the very complex way OpenQuake handled the sources is accompanied by a very useful handling of logic tree in the computation. All these new functionalities allow us to model something we were proposing in the last year as prototype. For example, grid sources that have a space and variable earthquake rates to account the situation at different scale. Two examples from Italy and a full issue for California. We can model interconnected fault rupture that have variable probabilities of occurrence in space and in time. And this is the exit of the USERF3 model for California, where the traditional time-independent model can be accompanied by time-dependent models or model depending on clustering statistics. There are also some other efforts done together with, let's say, data provider to work on interconnected for rupture that may have variable probabilities of occurring, exploiting the result in terms of risk or prototypes of risk, like the two recent papers here mentioned. But my main question, I leave you open for you, is where do we have all the ingredients for such a cake? Are we able to collect them in a proper way? Well, having a common jargon could be a good starting point, in my opinion. And so, because I'm not doing a traditional presentation, I do not write some conclusion, but I simply wrapping up the ideas presented before. And the ideas are those: hazard is not risk. We have some troubles when we look for a definition of seismic hazard that is acknowledged for the different participants to the hazard assessment. The distinction between deterministic and probabilistic is not so strict. And what is the standard level for all over the world, that is the third generation of seismotectonic probabilism, accept some basic assumptions that sometimes are not fully understood either. So more rigorous terminology is beneficial for all of us, technical communities and the general public. Moving toward the fourth generation, non-Poissonian probabilism, we can relax some assumption. We have new capabilities given by the latest probabilistic seismic hazard assessment engines. The ingredient has to be gathered with care and perhaps with a strong help by physics-based analysis. But probably we can extend this cake to many other places than the few ones represented till now. So I leave the floor for the 5th generation earthquake prediction or operational earthquake forecasting, as we quote right now, because there are of course, other people that can face this topic much better than what I can. I thank you for the patience, and if you want to deliver me some suggestion, comments, or criticism, please write me also after the end of this presentation. Thank you so much.
Thank you so much, Laura. That was really helpful and so clear at clarifying some of those differences. If anyone does have any questions, please do ask Laura aloud, or if you are unable to or would prefer to put in the chat, then do put in the chat as well.
Hi, Laura and Stefano. So thanks for the talk. Was very nice, and really nice to see such a comprehensive description. And I have to admit, I was surprised to see that the definition of hazard of a DPC, it's closer to the old Russian way of calculating seismic hazard than to the Esteva and Cornell way. So it's very much based on what is called shakeability. So on the looking at the potential intensity of ground motion that you have, and looking then for the magnitude or the kind of event that can generate it. So I really didn't know it, and I found it very, very interesting. I have just a curiosity to ask you, maybe based on your experience. I mean, time dependency in hazard is not new, for example. We have already models of time dependency going on since several years. The main problem is how to choose a good model and what would be the best model that we can use. So my question is, where do you think we are to this regard? I mean, to have models that we
do you want me to be honest?
Yes.
Do you want me to be honest? Really, I don't know where we are. I think we are progressing a lot by doing exercises in modeling the, let's say, short time dependency. That means modeling aftershock hazard, modeling ETAS model. But you know, these models work after you have a stronger earthquake. And probably we are not digging enough in the resources given by the paleoseismological community to do a step forward also in a more comprehensive evaluation of the complexity of the seismic cycle. So the efforts, and there are the efforts of the Fault2SHA community as well, is try to understand better the seismic cycle, to understand how we can process it into a computational way that has an output for society, like seismic hazard has.
Okay. Thank you.
Are there any other questions for Laura? I find it interesting, Laura, you went back to the Cornell approach, and we often see people referring to the Cornell approach, but completely incorrectly from what you clarified there. And why do you think it's been so misunderstood, or why do you think we all refer to it not quite correctly?
Well, I don't know. We are not so many connected right now, but if you ask people how many read the original paper, you have the answer. I mean, sometimes we continue to cite something because we have found it in our previous studies, and this is reasonable. But really, I understood the title of the Cornell paper, preparing this preparation, because in my mind the there was always the idea, okay, but why he's talking about seismic risk when he is producing a method to compute seismic hazard? It was always in my mind that there was a misunderstanding, and there is no misunderstanding, because he was really referring to the design level you need to have to protect people. So it was done in a risk perspective, but the computation is the same as you're doing now.
Brilliant. Well, thank you so much, Laura, for your whole presentation and for your answers to your questions. Really appreciate you giving us your time, and I'm sure everyone listening is now going away with a much clearer idea and what we need to do better in the future. So I just wanted to remind everyone that the next session in our learning series will be on the 14th of June, Monday, the 14th of June, a couple of hours later than the usual time to help. It's going to be presented by Yehuda Bock, and it's on measuring fault displacement hazards using GNSS. So he's over in California. So to help with him not having to have too much of an early start, we're going to be a couple of hours later. So I look forward to seeing you all in just over a month's time for that. And as I said, thank you so much to Laura. You're getting lots of messages in the chat saying thank you so much.
Thank you, bye.